Hey everyone. Okay, why my chat is don't show up? Why? Just touch myself. Why it is not show up? Why the chat is so? Oh, I'm stupid. Sorry. The chat is visible. Sorry, stupid. Okay. I think we're gonna ready for the Gaussian with picture. So I'm gonna move out the display, the primary monitor. So what's your good, everyone? Today's videos is about physics, and it's gonna be great. This is my first physics videos, and I already prepared something. I'm gonna see. Wait a minute. I'm gonna run my code first, and this is a lot of bunch of the mathematical. What the frick does it mean? Unexpected indents. Here we go. Wait. Oh yeah, that's what's right. Okay, here we go. This is the Gaussian wave package. Wait, why my screen look like this, bro? I don't want it. Wait a minute, I need to fix my screen first. Wait, why my screen look like this, bro? Wait a minute, guys. I need to fix my screen first. Okay, here we go. How to fix this? Okay, this is the Gaussian wave package I built in OpenGL here. Okay, I wanna give a tutorial how to make the Gaussian wave package, but this is not actual Gaussian wave package because Gaussian wave package is so complex. So let's jump to the equation. I'm gonna show you the equation. Okay, here we go. We're gonna do some sketch here. I'm gonna move you up first. I let's prepare my sketch. Where's my pen? Okay. The quantum Gaussian wave package. Gaussian wave package. What is Gaussian wave package? Okay. Okay, before we jump to the Gaussian wave package, we must know what is wave package. Wave package actually to describe the quantum particle in as a wave. Describe the quantum particle as a wave, like this. So the Gaussian wave package is we can see this the quantum particle because this is so small. You can't see that. You can't see the quantum particle because it's so small. So Schrödinger is like here make the equation is look like this. Sorry. So let me guess if I'm wrong. Okay, tell me if I'm wrong. This is a Schrödinger. This is a Hamiltonian, and this is the time depend Schrödinger equation here. So we're not gonna talk about this because we're gonna talk about this, the quantum wave package. Okay, wave package. The quantum wave package. I'm gonna explain again. Quantum wave package actually to describe the quantum particle to the wave. Before we have the Gaussian wave package, we have the wave package is using the Fourier transform here. Oh, sorry. Tell me guys if I'm wrong. I just remember some of the Fourier transform here. The frick is this? Sorry guys. There's something I need to tell me guys if I'm wrong. Like my equation wrong or not? Tell me. Just tell me. This is my first basic videos, physics let's explain let's term. So if I'm too wrong, so please someone tell me I'm too wrong. Oh yeah, I forgot to add the constant here. So sorry guys. A0 B0. I think there's something half here, like 1 over n, like this, right? Tell me if I'm wrong. Okay, this is a Fourier transform, and this is the earliest, because if you're using this Fourier transform, the wave is gonna look like this. This is the sum of the cos and the sin, because a cos of value is just down here. So if the wave is look like this, we can explain it. We can identify where is particle at, because to know where its particle is, we need the probability into that particle. So we need the probability of the particle. Sorry. The probability of the particle. If there's a look like this, you can find where is actual the particle is. So we need to use the Gaussian, because the Gaussian distributions curve is look like this. Oh, sorry. So if you look like this, we can tell where is a particle is. So if we calculate all of this range, this is 1. And if here, if vertical is the range of this value R and P here, this is going to be 50%. 50% chance of particle is in the rank E and B. So how we can combining this quantum particle with a Gaussian wave Gaussian distribution. Oh, sorry, I'm going to explain the Gaussian distribution first. Wait guys, wait. I'm sorry if my explanation is right, like no, you don't understand my explanation, so that's okay. This is the Gaussian distribution function for 2 pi this E negative x equals x min square root of divided by 2 standard deviation. Sorry, that's not x. To here. So this is the Gaussian wave function to make this the graph. What the frick is this, bro? So to combining this equation, we need the the another variance of the Fourier transform. This is the time dependent Fourier transform. So this Fourier transform is not a tab, because this Fourier transform is just freezing like this. This is not the time here. This is not depend on the time. So we're gonna use this type of the Fourier transform. Wait a minute, guys. I need to see something. Wait a minute. I think I explained something wrong. Okay, sorry guys, sorry. I don't care. No one watching me, because this my. Wait. Where's my awkward? Okay. We'll be back. Sorry. The frick is this? This is make so bad, bro. Okay. You're using this type of the Fourier transform. Wait a minute. Why is super next to that? I'm gonna move it. I'm gonna move it to someplace safe. Okay, this is time periodic the Gaussian wave figures. There is no time periodic here because there is no time here. So the next is we're gonna combine this with this. Okay. So in the physics, we need the energy. In the quantum physics, the particle have energy to move. the energy, the equation for the energy is p square or momentum into time the mass of the particle, and this is the momentum. This momentum mass and the particle. So, and we need the Planck constant too. Planck constant is around 2 point. I don't remember how many constant it is. Planck constant is so small. This normalized. This is normalized Planck constant here. So we need a time to the t is time, and we need momentum, and the x is position. And the reason we need to combine these two is because this equation. Wait. The delta p and delta x is greater than the Planck constant over the momentum here. So this is the unconservancy Heisenberg, and this equation is the limit of how far we can observe the quantum world. The limit is this Planck constant. So the reason we using the Gaussian wave package is to minimize this unconservancy. Okay, to minimize this unconservancy Heisenberg, we need to Gaussian wave package, because the regular using Fourier, this we cannot tell where is the position is, because we know the momentum. So the unconservancy Heisenberg is actually explaining we cannot observe the position if we know the momentum. If we know the position, we don't know how the momentum of particles. So to minimize it, we can know how where is it, the probability of the particle is. So yeah, guys, I'm sorry, I'm a bit nervous because it's my first time to explaining quantum physics here. If I'm wrong, you can tell me. You can tell me. So after we know the equation of the Gaussian distribution and the Fourier transform is a time Fourier transform, time oscillator Fourier transform. It is not, because it's gonna freeze it. We are get this equation. We already know how to get the momentum is. So we get this equation. Wait, guys, wait. I'm gonna move up. Yeah. I just check my steering, like if my steering is still run or not. I just worried. So the n is normalized I'm gonna explain later. I'm gonna rate it first. Wait. Wait, wait. I need to pick a one. Imaginary here, and P time R, and subtract by time over Planck constant here. Bam. Wait, I'm wrong. Sorry. Imaginary. This is imaginary. This is imaginary. So if you don't know, wait, it's not error. It's x e sin t here, and divide by Planck constant here. Tx, I think. Tx maybe. Because it's over x here. Okay, this is the Gaussian wave package. This Gaussian wave package here. So if we are just not supposed to like the expand this equation, we get this. Okay, we're gonna expand this equation. Wait, we need a more bigger space here. The n is this normalized constant. This normalized constant here. We can use the normalized constant is 2 time p and time the Planck constant here. So let's expand this to pi bar here, and the is p. We can use this is normalized, or we can use the things, but we're not gonna use it. E, we're gonna use normal. We focus here, 2 here, and oh no, wait a minute. 2 wait over divide by 2. It's gonna make this understanding here. Okay, this is constant. If we can use this as 1 over square 2 pi by 2 here. We can write that, or we can just give it a random number here. So, but that's gonna work. And the time is e. Wait a minute. We need to. Oh, this is the limit. Okay, this is the limit then. E. The time is e. Imaginary. We need imaginary to uploading that things. P times position, a momentum time position, and E time the time, divide by Planck constant here. So this is the explain. But if we wanted to do inside the Python, we can use integral here. We can use strike integral. So we can use the Riemann sum. The Riemann sum is actually like this. So this is a delta x, and this is the function. So the delta function, we can get the delta function by calculating a over b times the n. The n is how many data you have here. So you get the delta x here. So we're gonna rewrite to the Riemann sum here 2 by Planck constant here by n equals 0, and I don't know where this at, so we're gonna use constant here. I'm not gonna use the things, and the negative x a mean here, so it's divided by 2 here. So and the Px is E t here, and Planck constant and delta x here to replace this. Okay, and this is the final equation we're gonna use. But this videos is part 1. Okay, this was on part 1. I'm gonna show you the simple way. Okay. I want to show you the simple way. So I think, how can I make another? Oh, here another line. Okay, so we're gonna use just so very simple. We're gonna use this. Sorry, didn't need to. Why does this look like this? And again, we're gonna use this in Python. So this is simple. This is gonna use simple. This is we're not gonna use this or to be 0 or be this. Okay. Okay, let's get to Python to the practice it first. Okay, we're gonna change to the Python. Okay, we're gonna delete this. I'm gonna delete these things. Delete everything, or maybe we can just comment it. Okay, the use z-axis. We're gonna try to give the cost first. NP dot cost first. Okay, cost of x plus y here. Let's see how the 3D graph is cost. Okay, where is this? Why is this not showing anything? Okay, I think that's like, oh no, that's not like. Okay, here we go. I want to get the cost function here. Wait, why is this not showing anything? Okay, here we go. Here we go. I need to be more patient. This is the 3D plane. The 3D. Oh man, it's so like, bro. Why? Wait, guys. Wait a minute. My computer is so lag, bro. Okay, here we go. This is a cos. Okay, this is a cos in the 3D plane. 3D crap. I use OpenGL to make this, bro. You can download my code later after the stream end. Okay, here we go. This is the cos. What if I add it with the time? Let's see how this goes. And the cos paper is moving like a wave. You see that? This is so slow because my computer is getting handling these things. That's crazy. See that that's moving, like the wave is going from state A to B. And if you see in the top, you're gonna see that things. It's like some winds is just blowing from the other direction. And what if we add it with a sin here? Add with a sin. What happened? Let's see. What happened when we add a sin here? And the graph is becoming the combining of sin and cos wave here. It's moving so very big here. There is just have a big wave and a plane here. So this does not look like the Gaussian wave figures at all. That does not look like the Gaussian wave figures at all. So let's try to making this into the Fourier. Let's time this with a P. And time it again with how many of this type is with the grids. With the grids is 47. This is just the dot. This is moving, like not actually like the plane, but it is the dot right here. And I need to loop the section to generate the things because that was just dot. See that? This is just point, just dot point. So try to grid here and do it to wait a minute, and divided by the length. The L is a Fourier transform is actually the length. Wait, I'm not explain that right. I don't explain that things. Wait a minute, let me change the monitor first. The L is actually length. Okay, the length of the wave. Remember guys, this is not an actual Gaussian wave figures. The actual Gaussian wave figures equation is look like this. This actual Gaussian wave figures is look like this. So okay, let's move into my primary monitor. Okay, we're gonna continue this. and like the width and the length, like the length is the half of the biggest. Way big we give it, we gotta give it the wave is so very flat, because if you're gonna close to the actual range of the theta, the range of theta is 5. Okay, if we're gonna become close to the range like 5, the wave is going to become so very flat, because the actual length, the divided with actual length, just become the 1. Okay, that is not going to give it anything, so I'm going to give it a half. So let's put it into the scene here. Boom. And let's see how this goes. Okay, boom. And this is look like this. It becomes so very fast. It's moving so very fast here. See that? It's moving very fast, and yeah, moving very fast. And the wave is look like this, because it's only 2, and the wave is become so close to the 1. So if we give it the 1.5 here, wait a minute guys. Okay, here we go. This become way more higher, but this is become so very fast, moving here. The move so very fast, because the time is I put a 5 here, so I'm gonna change it later. We're gonna focus on to building this, okay? Or maybe we can just do like time p by these things. There you go. We're gonna do this. We're gonna just divide this by the splitting the x and y into different coordinate here. Let's see how this changes. I want to see that. Okay, it's just become the actual wavelength, because I'm not combining, and this is the actual wave length here. Okay, this is our actual wavelength, because I'm set 1.5. Okay, because I set it in 1.5, the length is so very sharp, not flat, not become flatter. So after we successfully to build this further wave packets here, okay, we don't need to integral or the Riemann sum. The next is we're gonna build the Gaussian here. Maybe I'm gonna add a lambda, but no, I'm not gonna use a lambda here. So let's just this time. First, we must be at the constant here. Constant is 5, because 5 is the maximum value of the theta here. And it's the np dot exponent here, because we need the exponent to wait. We need exponent. Remember the equation of the Gaussian distribution. We need the exponent here, so we're gonna use the exponent with no imaginary number here. Okay, we're not gonna add the imaginary number, because we're gonna add the imaginary number in the next stream. Okay, wait me in the next stream. Okay, crazy thing, no one watching me when I'm trying to explain the physics here. Yeah, I don't care to. The negative of x, the power of 2 or x squared is plus t. We're gonna just minus it with a min. Wait. And with the min of the x here. We need two of this because this is gonna not enough. We're gonna add again with a u value here. Wait. Gonna take here and the weight value here. What is this? Why is this error here? Oh no, it's not error. And we're gonna divide after all of this. We're gonna divide by, wait, where is this one in here? Divide by 2. We're gonna add the random here, and without sin, we're gonna use sin, bro. Instead of a standard deviation, we're gonna use sin, because sin gonna give the bigger value than the standard deviation. You know what I'm saying, right? Or maybe you're gonna using standard deviation instead of sin. Standard deviation of the x plus add with y, add with the time here. Why is error here? Okay, this error is gone. So let's see the final wave. Okay, here we go. This is the Gaussian wave package. It's simple Gaussian wave package, not actually Gaussian wave package. But why this is the decreasing and the con? Wait, we need to change it. I think we're gonna edit with the here. I think the problem is this. This is a problem, maybe. Let's see again. Oh wait. Oh, here we go. This become normal. Okay, let's become normal wave package here. And here we go. This is the Gaussian wave package. And done. We don't make it in part 1. In the part 2, we could actually make the actual Gaussian wave package in the 3D space here. So subscribe. Don't forget to like, comment, and subscribe my channel, guys. Waiting to another stream. So yeah, thank you for watching. See you in the next stream, and goodbye.